Hello, everyone. So yes, I'm Bethany Macri. I'm a data platform engineer at Etsy, and I'm going to be talking to you today about 3 major infrastructural projects that Etsy accomplished in order to scale. So first, who has heard of Etsy? I'm never quite sure about the familiarity in the room. Okay, so most people know. For those of you who don't know, Etsy is an online platform that allows people from all over the world to buy and sell handmade and vintage goods. So a little bit of background. Here's some statistics. We were founded in 2005 and have grown immensely since then. We have approximately 800 employees, 1.5 million active sellers, about 23 million active buyers, and we transact in nearly every country in the world, which means as we've grown, we needed to scale such that we can support multiple languages and transacting in multiple currencies. We've expanded our offices as we've grown. Here are some pictures of our offices around the world. As I said, we have about 800 employees. So my point in discussing some of these numbers and showing you our locations around the world is sort of to provide a cultural backdrop for the reasons for having to adapt our infrastructure in order to scale. But before I get to that, now that you know a little bit more about Etsy than maybe you did before, I want to talk a little bit about Etsy's engineering. We run on a LAMP stack, we are monolithic, we are multi-platform. Our engineering motto is code as craft. In addition to following the apprenticeship model of a craft, where more senior people will kind of take more junior people under their wing and bring them along, which Etsy does quite well, I think there are at least 3 things that Etsy does exceptionally well as we hone our craft. The first is that we practice continuous integration. We push the site roughly 35 times daily. A push is not a release. The thought behind this is that it increases the safety of our system to push in small increments. A small change is easier to write, it's easier to have code reviewed, it's easier to test, it's easier to understand, and it's easier to fix. Failures are kept small because changes are small, or in the event that failure is catastrophic, the change is easily identified and reverted. The second thing we do quite well is that we measure everything. We are a metrics-driven organization. This means that we measure everything and we graph what we measure. We then alert on our graphs, whether through automated pages or by being able to easily spot anomalies. The final thing that is less technical and more a cultural part of our engineering organization is that we practice blameless postmortems or retrospectives. This is a huge part of our engineering culture, and not only do we encourage blamelessness, we do not tolerate blamefulness. This does not mean that no responsibility is taken when, for example, an outage occurs. What it does mean is that rather than pointing the blame at an individual or set of individuals, we examine the event as a failure of the system that we have together created, and we investigate the set of circumstances that allowed the failure to occur. So in addition to the cultural pieces that I've just discussed, there's also a specific technical story to tell around how we've scaled since our small Brooklyn-based company in 2005. So this talk is a retrospective in which I will tell that technical story. I'll reflect on 3 major infrastructural projects that we've accomplished in order to scale. But first, what do I even mean by scale? What am I talking about when I say the scalability of a system? The most relevant definition I found is scalability is the capability of a system, network, or process to handle a growing amount of work, or its potential to be enlarged in order to accommodate that growth. So today I'm talking about growth in terms of number of users, and therefore increased traffic and increased data that we would have to store. More shops, more listings, more images. Growth in terms of the complexity of our code base. Growth in terms of the number of engineers, growth in terms of the number and complexity of features that we would support on the site. So I'll be talking about 3 things that we did in order to optimize this growth. The first is sharding, the second is our API, and the third is what we call Project Arizona, and I know that sounds very mysterious right now, but I'll get to it later. So the first is sharding. In the beginning, we had one Postgres database with many tables. This presented several problems for us. First, it was a single point of failure. We experienced downtime when we failed over to the secondary during an outage or during a schema change. Secondly, the schema of this Postgres database had stored procedures in it. As I mentioned before, we practiced continuous integration, and these stored procedures were very difficult to test and very difficult to mesh with our continuous integration environment. We also, at the time, were running this database on the best hardware that money could buy, so we literally could not scale vertically. And there was a bad experience. So a little bit of backstory. A lot of Flickr's engineers, so Flickr is the photo sharing site, I'm assuming most people are familiar. A lot of Flickr engineers came to Etsy. Now, at Flickr, when President Barack Obama was running for president, he created a Flickr account, and it flooded Flickr's database and took the website down. So the Flickr engineers said, never again. We'll split our data onto different databases, and then in this way, we'll hedge against one user becoming hot and taking the site down by allowing ourselves to easily migrate the data of a user that has become super popular. So when those Flickr engineers implemented that at Flickr, it worked for them. They came to Etsy, they implemented it at Etsy. Except the shards do not look like this, because who could find anything in this mess? They look more like this. We have A/B pairs for each shard. It's a primary-primary setup. This is called master-master by some. We chose to shard this way so that you could load balance the writes and reads on both sides that you have set up. I just need to take a quick drink. So let me show you how this works. A request comes in from the internet, hits our PHP application. We go get an ID from what we call the ticket server, and I'm going to zoom in here because this is important. Side A of the ticket server has only odd numbers. We accomplish this with a simple increment2 statement in our MySQL schema. Side B of the ticket server has only even numbers. Requests are routed randomly to side A or side B, and in this way, we're able to guarantee globally unique primary keys. This is crucial for sharding because we need our primary keys to be unique in the case that we need to migrate data. We then go to index, which is effectively a lookup table, and record on which shard we will record the data. You will see that like the ticket server, index is represented here by two databases, because in fact it is two databases. The purpose here, though, is redundancy in the event that we need to fail over. These replicants have a master-master relationship, and the side we write to is picked randomly. Finally, we write to the shards. You'll see here that the shards are also replicants. Remember what I was saying about the importance of globally unique primary keys generated by our ticket server. Our MySQL shards are master-master replication pairs for resiliency, but it also enables us to do seamless schema changes. So let me show you that. For a schema change, we'll take side A out, apply the schema change to it. Meanwhile, side B is serving requests. Put side A back in, take side B out, apply the schema change to it, put it back in. So sharding allowed us to scale our database horizontally, giving us both resilience and performance benefits, and better integration with our continuous integration environment. This is important because our data is the beating heart of our application. Our customers depend on it, our customer support team depends on it, our financial reports depend on it. Our product engineers depend on performant, easy access to it. So without a proper API in place that would enable product engineers to access this data, sharding would be a useless project. And that's why we wrote the current version of the API, API v3. So first, let me talk a little bit about v2, because there were good parts to it. v2 followed a fairly traditional model view controller setup, where a request comes in and gets routed to a controller, gets data from a model, the data populates a view, and the view gets rendered in a response. Now, stepping back to the data access layer a bit that I was talking about, each database table that we have has a corresponding model table. Has a corresponding model called an Etsy model. API v2 was written to make it easy to take an existing Etsy model and make it available via a JSON HTTP API for CRUD operations. Each Etsy model can establish relationships, either one-to-one or one-to-many, to other models using associations to mirror relations in database schemas. So for example, this is an association that you would see on the listing model. It's associating to the listing shop by the ID, shop ID. In the V2 framework, these associations were exposed as include parameters to endpoints. This meant that a client could request a shop and additionally ask for the listings from the shop to be included in the response. Both shop and listings would be returned in the resulting response, saving the client from making a second HTTP request. Includes and field parameters turned out to be a very powerful concept for us, for those people who were writing API clients, including our own mobile native apps. So powerful, in fact, that when we released our first iPhone app, no new API endpoints were required to support it. Everything could be sourced from existing endpoints with appropriate include parameters. But with the good comes the bad. Several aspects of V2 presented some issues when it came to supporting the API long-term for us. These same include paths. So though associating objects via include paths was amazingly useful for clients, this flexibility also had implications when it came to server-side performance. Because a client could control the complexity of a given endpoint via request parameters, it meant that runtime latency measurements had huge variance. For example, in the 95th percentile of a given endpoint, if it increased, it wasn't immediately clear if this was related to an overloaded backend data store or to a client who suddenly started requesting additional included resources. Secondly, mapping to schemas. As API v2 made it very easy to expose an ORM model as a RESTful API resource, it meant that the schema of the API was a snapshot of the model at one point in time. This one-to-one mapping posed problems when we subsequently performed data migrations and restructured the data of the model. Additionally, because there was some implicit framework magic arising from reflecting on a model to determine the endpoint behavior, it made it more involved to unit test endpoints. I'm thirsty today, excuse me. There was also an issue of duplicated logic that wasn't a requirement of V2, but it was a result of it. So let me show you what I mean by duplicated logic. We have the web. Product engineers would build a web controller to format the data into something that could be passed along to a template and then rendered in the browser, and then add business logic so that they could access the data in the database. Then mobile applications were sort of a secondary concern and an afterthought. They'd build multiple endpoints with V2 to get all of their resources, then use different business logic to access the data in the database. And we would end up with this awkward split, where the integration or common point was the database. Some of the business logic of the layer was shared between them, but a lot was duplicated. So you see API v2 led to developer bad habits, primarily adding business logic to controllers rather than models, and in pathological cases, we were doing fetch queries from templates, which is a big no-no. This meant that logic had to be recreated in API v2 endpoints, leading to potential inconsistencies and missing functionality otherwise available on the website. So we needed a total shift of mindset. This was a cultural problem. People first built features for their website, and then they built features for our native applications. And this was perhaps the biggest problem and the biggest disconnect from reality in our mindset of our present and our future, because we weren't in this world anymore, which is to say, we were not in a desktop-only or even a primarily desktop world anymore. We were in this world where the majority of our traffic was coming from mobile devices. And our API powers our native applications on iPhone, Android, iPad, et cetera. And in this world of clients making requests from mobile devices, we were losing too much time making HTTP requests around the world. We had the ability for the client to ask for associations and include paths that were relationships between resources, but you couldn't do such thing as, for example, get a listing and know whether the browsing user of that listing had favorited it. So the iPhone app, in order to get this, would have to make at least 2 HTTP requests. In fact, for most client views, you had to make more than one request, and this added up to a lot of latency from our mobile applications. So as I mentioned before, we are a LAMP stack. Much of the application is written in PHP. PHP, as you probably know, is single-threaded, short-lived, shared nothing. This is beneficial because it limits complexity, but it creates a tension because we want to be able to do more things at once, and we don't have opportunities for concurrency in PHP. So as our application gets more complex, we end up increasing the lower bound of our request time because more things have to happen. So how do we accomplish concurrency with PHP? Spoiler, we don't. But with this problem in mind, one of our engineers, who actually is at this conference today, went to Netflix to spend some time with their API team. They have a much bigger proliferation of devices. They support probably thousands of devices. And so we wanted to see how they had solved this problem. They decided to have their API team not support all of these devices, but instead give the device teams the ability to change their API to match their requirements for a given feature. They offer a thin scripting layer on top of their API so that the device teams can write APIs only for what they need. From this visit, this particular engineer brought back 2 ideas that would be the building blocks of API v3. This was the idea of 2 kinds of endpoints, component and bespoke. They together gave their device teams the ability to change the API to match their requirements. So we had this new idea, but we embrace our monolith, and we are sort of famous for having an aversion to services. So we decided not to recreate the wheel and not to make any huge changes to the system or do any huge rewrites. So we decided we'll keep having PHP execute requests in a sequential fashion, but we'll make HTTP requests in an asynchronous manner, such that when one request comes in, PHP starts working on it, and it can farm out work using asynchronous HTTP, saying this is all the things I want doing, and it will just sit there waiting until the slowest request comes back. We were able to do this with curl multi-init. So in our own data center, we were making HTTP requests to our own API, and I'll show you how this works later. But first, before I show you how this works, I want to show you kind of what I'm talking about and what kind of things Bespoke powers. So this is Bespoke from our homepage. New from your favorite shops would be an example of a Bespoke endpoint that fans out and gets all new items from your favorited shops. The same goes for updates from shops that you like. So how does this work? A Bespoke endpoint, a request comes in, hits our Bespoke API, goes to the cache. Any cache miss then goes to our component API, and then to the server. So why is this better? It's because all of this happens within our own data center. So we are no longer making the huge round trips across the world, and we're also able to monitor performance of our mobile calls because we know exactly which routes map to certain endpoints. Plus, the v3 approach that we were doing is saying, all right, everything now runs out of the API. We're doing API first. So all native clients will make the calls, and the website will make calls to that API and then use the resultant data to render the HTML. So we now have an API that can be at the center of our product development. So here's a Bespoke endpoint. I just wanted to show you an example quickly, point out a couple of things. First, the route is specified. So unlike v2, where I was mentioning those include parameters, you now know that one endpoint always matches one route. This makes performance monitoring as well as unit testing much more straightforward. So here's where we build up values that we will later use as our component calls. And here's where we execute resolve on each statement. So resolve is just effectively a non-blocking HTTP request to each of the values, which remember our client calls passed in as arguments. Lastly, I just want to call attention to the fact that this endpoint is an implementation of an interface. This made sense because it made v3 easier to write. It's also much easier to debug. So by writing a new version of our API, we made it easier for our product engineers to access data and iterate quickly on our products. It was easier to write. You only had to write one thing in one place, and it allowed us to write more features faster. It also enabled us to scale in terms of the devices that we supported. We were building for mobile devices in addition to the web now. Perhaps most importantly, it made our native app calls faster. But a problem still remained. And this problem is for any company operating at scale, and that is, what are you going to do with your so-called big data? So here we get to datasets v3. We have a lot of data stored on our shards, and as I mentioned, we've taken great care to ensure that that data is accurate and accessed in a performant way. But we also want to make use of this data in a unique, meaningful way for our customers. We want to take that data and be able to perform analysis on it in such a way that the customers can view it in a new way. An example of this is recommendations on Etsy. That's probably our best example of a big data job. Our data scientists write Hadoop jobs that are stored in HDFS, the Hadoop file system. As soon as the data is stored in HDFS, we call it a data set. Now, Hadoop itself is very useful for analyzing data and generating aggregate data, but the read latency on Hadoop is very high and, in fact, unacceptable for our website SLA. So to give you a sense, it's over 2 seconds. This kind of latency would be unacceptable. The implied solution is moving the data off of HDFS, but to where and how will we move terabytes of data and millions of rows? We could have used the shards. However, this operation would have had to have been heavily throttled. We can't just load millions of rows into the shards through a fire hose. That would cause performance problems on the shards. This would also require a schema change every time you wanted to make a change to a data set. And remember, the shards look like this. They're primary pairs. Inserting millions of rows onto the shards would have caused enormous slave lag. Even though our sharded architecture isn't set up as master-slave, until a record is written to both sides, the side that has not yet been written to is technically the slave of the other side. We've also considered Redis. So for those of you who don't know, Redis is an open source key value store. It's effectively a data structure server. So Redis has really good parts of it. It was fast to read data with Redis because it's an in-memory store. We were not, at the time, considering Redis persistence. It's open source, and it was an out-of-the-box solution for us. But again, with the good comes the bad. Like I said, it's an in-memory store. And that is the reason that it's so fast. This caused problems for us because when we ran out of space on the Redis cluster, the box would go down. And it would take us hours to bootstrap that data again because we had not persisted it. We also, at the time, did not have much operational experience with Redis. We actually do now, and I think a trial of this would be more successful now because of it. It's also expensive to scale memory. So given the issues we had with Redis, we faced a problem of how to continue to support data sets at Etsy. So with that challenge in mind, several engineers went on a retreat to the state of Arizona, where one of our remote engineers lived, and they called their solution Project Arizona. The constraints of the new system were that it had to scale beyond RAM, it had to be consistently fast, and it had to handle nightly bulk loads from Hadoop. So this is Arizona. It's effectively a giant state machine. So I'll walk you through the path of how we get data sets from Hadoop to be accessible from the web. Hadoop job is synced into the Hadoop file system. Sadly, as I said, Hadoop has too high of a read latency, so we can't read right off of that. It also cannot bake SQLite files, and I mentioned SQLite preemptively here. I'll get back to that. But SQLite files cannot be written on a streaming basis because they need local storage, and that's not available in Hadoop. So at this point, a data set is set to status generated. And a row in this table is created. So this is getting into the state machine that I mentioned. A box, the Arizona transformer, then pulls what we call the conductor API, which is actually a collection of v3 endpoints for data sets whose status has been marked as generated. Once it finds them, it copies, It copies data from the Hadoop file system onto the transformer. At this point, the dataset status is set to baking. And here is where we bake the Hadoop part files into SQLite files. Once the dataset status has been set to baked, it begins shipping to the Arizona servers. The status is then set to shipping. Once it's on the Arizona servers, its status is marked as shipped. We then flip a symlink, and its status is set to serving. So this as a whole is what we call Project Arizona, and this was our solution to serving big data at Etsy. By creating a resilient big data pipeline, we were able to scale what data sets meant at Etsy. We could now store more data sets on the datasets servers and still access them consistently and quickly. This was an advantage to us because not only could we build more features that requested data sets, it also allowed us to store multiple versions of the same data sets in production. In this way, we could roll back in case of error. I would offer that it also allowed us to scale in terms of what we were able to offer our customers, who could now have a more curated experience on the site. So now that I've told you about these 3 infrastructural projects, I'd like to do some reflection. As I mentioned early in the talk, at Etsy we conduct blameless postmortems. As such, we are extremely conscious of using what's called counterfactual language. An example of this is, if I had known X, I would have done Y. The fact is, we didn't do what we should have done or what we would have done if we had more information or what we could have done. What I've detailed in this talk is what we did. And while I hesitate to be counterfactual, I want to share with others what we've learned through our scaling journey. If you remember this slide from early in the talk, what just ship means to me is an encapsulation of lean software principles, specifically eliminate waste, decide as late as possible, and deliver as fast as possible. I think that this mentality has enormous value, and I believe it still shapes, in large part, our engineering culture. However, I believe that it comes at a cost, and this may make me unpopular, but I believe that code hygiene, tests, standards, design patterns, thinking about how technical debt will incur and who will pay it down and how it will be paid down, become more important as your organization scales. You also may have noticed that each of these projects were not the V1. In fact, 2 of them were V3, and that's the API and the datasets. None of them were our first draft. I believe Donald Knuth said it best. Programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs, and these attempts at efficiency actually have a strong negative impact when debugging and maintenance are considered. We should not forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. My point here is that your organization needs to live in order to know what that critical 3% is for you. So I hope that Etsy's story has been helpful to you. You can find us and more about our projects on the web at GitHub and at Code as Craft. And we are hiring. And thank you. Any questions? We have a break after this, so you can come find me too. OK. Yes? They take about 6 hours to bake, and there really is no typical size. So it's on average 6 hours, but it depends on the size of the data set. Oh, terabytes. In fact, we have, on each of those Arizona servers, we have 10 terabytes of disk space because they take up that much room. Yes? Yeah.
Oh, hey.
Hi.
Thank you. That was fantastic stuff. I wanted to just see if I understood how you're using SQLite databases. Are you using it effectively as like a caching layer in front of the data sets? Is that right?
We're using it as a database. I wouldn't say it's a caching layer because it's all persisted, but it does. I see what you're saying in that it is effectively fronting Hadoop in between the web. So I think I think you understand. Any other questions? Cool. Thank you very much.